that this is a direct question. So sometimes students believe that direct question would not be asked in the exam, but there are some direct questions. I'm just asserting its a statement that potential drop across any portion of conductor is directly proportional to length of that portion, provided constant current and constant area of cross section. So a typical diagram is like this. Some resistance. This is an optional part. You can put an ammeter here, and then there is potentiometer wire, namely AB. And in order to find EMF of a cell, we have to connect cell in this way, positive, and this is called driver cell, and this is experimental cell. So here we connect a galvanometer, and from here we touch it on different points. So complete theory is given in my another video, theoretical explanation of entire this. So kindly check to that, and it's a direct question, so no need to worry about it. And in the same way, there are some other direct questions here. Describe with the help of circuit diagram how potentiometer is used to determine internal resistance of cell. So once again, working, I'm leaving with that video in which I have explained its working, only just for a recall, so that you can easily distinguish, you easily identify which video you have to watch and see. In order to find internal resistance, here a high resistance also connected, and a galvanometer. So this is how we can connect. I mean, there is some external resistance there for this secondary circuit. So that's all. And once again, we will write here driver cell, here experimental cell. That's all. State the principle of potentiometer. How is it used to compare EMF of two cells? So once again, it's circuit diagram. Oh, I forgot. This can be variable. So and in order to compare EMF of cells, you have to connect two cells one at a time. So this is how. Next, potentiometer is equivalent to an ideal voltmeter. V is the structure for voltmeter. Justify. So actually, a potentiometer is a device which measures potential difference, EMF, in null deflection condition. So since potentiometer is based upon null deflection method, so at null point it acts like a voltmeter having infinite resistance, which is the requirement of an ideal voltmeter. That's all. So basically, an ideal voltmeter should have infinite resistance so that no current should pass through it. And this is what happens with potentiometer. At null point, at null condition, no current pass through it. So at that time, it meets the requirement of an ideal voltmeter. But of course, potentiometer is not the voltmeter, but we can say it is fulfilling the criteria for a device to measure potential difference, especially EMF. What is the sensitivity of potentiometer? How can we increase it? So sensitivity of potentiometer is sensitivity of potentiometer. It is the measure of how small change can we detect for a change, oh god, in voltage can we detect for a large change in length. So in comparison to length, if we are changing the length, changing the position, uh, and we are obtaining different voltages, so how small voltage change can we detect over a large distance or larger length? So it means, so sensitivity is inversely proportional to potential gradient. Potential gradient often denoted by K or K. So where K is equal to voltage upon length. voltage of across entire wire, length of entire wire. Or also we can say I rho by A. How this has come, you can check the basics of potentiometer, you will come to know. So how can we increase it? So first method is by increasing length of potentiometer wire. This from first expression we can come to know about it, that if we increase the length then K will decrease. If K will decrease then sensitivity. Okay, and the second thing what we can do is by decreasing the current, by decreasing the current. So here in the potentiometer circuit shown here gives balance point at X. How will the balance point shift when R increase? If R increases, then current in this circuit, potentiometer wire circuit, will decrease. And if it decreases, then potential difference across AB decreases, and hence potential gradient will decrease. So therefore, this balancing length will change. So how we can do that? So we know that since E equal to KL. Okay, so if R increases, then I through AB decreases. So V across AB decreases, and hence K, that is equal to VAB upon LAB, decreases. So E equal to KL, in previous case I am calling it K dash now, K prime L prime, which implies that since K is K prime decreased, so L prime increases. And if L prime increases means X will shift toward B. This is the first thing. So remember, EMF will remain same. So earlier it was KL, but now it is K dash L dash. K has changed, L will also change. K decreased, so L will increase. So that is why X will shift toward B. Next, okay, second part, S increases. So there's no effect of this resistance. Why? Because at null point, no current flows. So presence of S will not affect that position of X. One can ask that why even then this resistance is placed there, connected there. So this resistance ensures that there will be a very less current, so that we can easily detect null point. Now this question, it looks like it is a potentiometer type question, but it is simply a circuit based, a series parallel type question. Resistance R draws current from potentiometer as shown. Okay, this. So okay, wire has resistance R naught. All right, so actually I didn't mention here, this is R actually. So derive expression for V across R when sliding contact is in the middle of potentiometer wire. This V, not to be confused by this voltage, I'm writing voltage. For the voltage I'm writing. Okay, so it will come in terms of this V. So I'm in order to avoid confusion, I'm writing it V dash voltage across R when sliding contact is in middle of potentiometer wire. Now see, I'm redrawing this circuit as some V voltage, and actually series parallel concept is dropped this year, but still question can be asked in this way. They can say that this is the potentiometer question, and how can we run away from such kind of questions when current electricity topic is there? So now you can see it is like this. So we have to find potential difference here. So what will the method? first I am solving out. I am writing marking it R1, it is R2, and it is R3. Why is it required? So that we can easily tell that R1 R2 are in parallel. First step. So 1 upon R12 is equal to 1 upon R0 by 2 plus 1 upon R. So that is 2 upon R naught plus 1 upon R, and that is R naught R, and 2R plus R naught. And therefore R12 is equal to R naught R upon 2R plus R naught. And now it is in series combination with R3. R12 and R3 are in series. So R123 is equal to R naught by 2 plus R naught R by 2R plus R naught. And now we can apply V equal to IR. So I equal to V upon R, V upon R123. So that is V upon R naught by 2 plus R naught R by 2R plus R naught. And final step, we have to find this V dash which is across this, means entire combination, both are in parallel, so in parallel voltage remains same, so very less space is there. This is separate work. V dash equal to, I expected that I could be able to solve it here, but anyway, sometimes it happens. So I and R12 actually, I'm using this part also. So okay, so you can see I is this one, V upon R naught by 2 plus R naught R by 2R plus R naught multiplied by, actually this is the value of V dash, V prime in fact. R12 is R naught R upon 2R plus R naught. If we multiply it here, then it will be V R naught R upon R naught 2R plus R naught upon 2 plus, both will get cancelled, R naught R. And if we take LCM of this 2 will go in the numerator. So it will be 2V R naught R upon R naught 2R plus R naught plus 2R naught R. R naught can be taken as common and they will throughout cancelled. And finally what left is 2V R upon 2R plus R naught plus 2R. Actually this R naught was taken common and cancelled. We can do this mentally. And finally what left over there, 2VR upon 4R plus R naught plus R naught. So that's all. Next, in a potentiometer wire, why is it necessary to use long wire? First, answer to first is to increase sensitivity of potentiometer. Since sensitivity is inversely proportional to potential gradient, you need to write it in full. I use these symbolic representation, but you need to write it in full. And potential gradient is VAB upon LAB. So sensitivity, I'm again writing it in short, so that is 1 upon VAB upon LAB. So this is directly proportional to LAB upon VAB. So that is, it is directly proportional to length. So that is why if we increase L, sensitivity will increase. Second, have uniform area of cross section. So second point, according to principle of potentiometer, V is directly proportional to L. Now since V equal to IR and R equal to rho L upon A, now if A is same and I also, then only V is directly proportional to L. And lastly, EMF of driver cell greater than experimental cell. So there is very less space, and I think I have to drop down this question. So answer to this is If EMF is less, then we can't find null point on the potentiometer wire, because at that condition deflection in the galvanometer will be in one direction only. So here I came up with a solution to solve this out. It is looking like a call out of a comic book. Alright, in a potentiometer experiment, if area of cross section of wire increases uniformly from one end to other end, it is like if wire is of this form, area of cross section is increasing um, uniformly from one end to other, draw a graph showing variation of potential gradient with L. So how will potential gradient change across this wire? Interesting. All right, now we will start it from here. Since R is equal to rho L upon A, it means, so along the length R will decrease, and therefore, and also V will decrease. So potential gradient is equal to V upon length. This length should not be confused with this. This means the position from here to here. So this is a variable distances here. L. This is a variable. And here, if I write it like rho L upon A, rho upon A, it will be. So that means it is inversely proportional to area of cross section. And as area of cross section increases, so also, because across the wire, along the wire, area of cross section is increasing, so potential gradient will decrease. So if we will draw a graph on moving from tip to this end to this end, so with increase in L, actually this is not the graph between potential gradient and area. This is the graph between potential gradient, how it is changing with length. Actually, with this length, area of cross section is changing. So here, area cross section was this, here it was this, then here it was this, here it was this, and so on. So potential gradient is varying from part to part, and on and on and on. So it will decrease like this. Here at very beginning, where L is 0 for this much small portion, it is undefined, yet its graph will go like this. So this question, it looks difficult one. Yeah, it is a little bit. Yeah, of course. So a potentiometer wire 1 meter long connected to a driver cell 3 volt. When a cell this much used in secondary circuit, this circuit balance point found to be 60 centimeter. On replacing this cell using unknown cell, balance point shift to 8. Actually, it was 80, I guess. So calculate unknown EMF. Very simple question. Very simple question. E1 upon E2 is equal to L1 upon L2. That's all. E1 is 1.5. Okay, one can be confused here. Actually, it is driver cell. Generally, this driver cell is not included in entire these calculations. And if we talk about the application part or uses of this potentiometer, so you can see the EMF of driver cell is not used in any of the formula. But yeah, it doesn't mean that this part of the circuit is not used. There are some questions in which this part will also be used. So I will tell you about it later on. But before that, okay, E1 is this, E2 we don't know, L1 is this, L2 is this. And from here we can easily find E2, which is equal to 1.5 into 800 cancelled out upon 6, I think. Yeah, of course. So 1.5 4 and 4 2 2 volt. Now explain whether circuit works if driver cell. Answer is no, big no, because otherwise we will not be able to. I'm not writing it, but I'm saying it, that otherwise we will not able to find null point, because each time galvanometer show deflection in one direction only. What is the use of high resistance? Okay, it ensures low current supply in experimental cell circuit. In short, I write CKT. Yeah, that's good. Okay, it ensures low current supply in experimental cell circuit. Okay, does high resistance affect balance point? Answer is no, because final reading is made, or we can say null point is detected at open circuit condition. Okay, next. um, what will you, oh my god, oh, purposely I wrote this, I have written this. What will you do if you failed? Oh, it's not complete, don't write any answer, any wrong things. We will repeat, we will kill our teacher. No, don't do that. We will find physics bug. And anyway, so if you failed to uh, to find null point, so few things can be done. Check the circuit connectivity, circuit connections. Second thing what you can do is increasing sensitivity by increasing length of potentiometer wire, or increasing sensitivity by decreasing current in potentiometer wire. So in the adjacent circuit arrangement, null point obtained at a distance 300 centimeter, 120 centimeter. Okay, when both are in same direction, then it must actually, diagrammatically I drawn it wrong. It will have to go long distance, and when they are opposite, they must be cancelling each other. So less will be the balancing distance. Find E1 by E2, position of null point for E1. All right, so let's do it. So in case 1, it will be E1 plus E2 is equal to K. Actually, I'm doing it directly. This one, actually, both for both, K will be there. So K will get cancelled. So E1 plus E2 upon E1 minus E2 is equal to L1 upon L2. And that is E1 plus E2 upon E1 minus E2 equal to 300 by 120. So which will be equal to 5 by 2. And now we can cross multiply and all that. There is another tool which is called dividendo componendo. So I hope you people are getting it. Oh my god. Otherwise you can do that thing also, just cross multiply it, rearrange, and then find E1 by E2. I use this way. So as we did here, we will do here also. So now it will be 2E1 upon 2E2, and that is equal to 7 by 3. So E1 by E2 is 7 by 3. I'm doing it here. E1 by E2 is 7 by 3. Okay. Next, potentiometer is used to determine internal resistance. Oh, a cell in experiment. Where, mm, when experimental cell is in open circuit, null point is observed at 260, and when it is in closed circuit. Okay, maybe in faster I did some mistake, but all right. So with resistance 40 ohm, null point observed at 120. Okay, and let me tell you here, it is the theory behind this. So what is happening here, in order to find, sorry, here internal resistance, first we do the experiment with the cell and find this expression. Then we we connect it with some resistance, so that a potential difference is set up here. See, when there is no resistance, then EMF is obtained. When there is a resistance, then potential difference is obtained. And after solving both of them, we conclude. How is it happening? Watch the video of theory of this. Link is in the description, and then you will be able to understand. Here I'm directly writing the formula. This will be the formula used here. So what they are saying, that when it is in open circuit, this is the open circuit condition. So then L1 is we are obtaining L1. And when it is in closed circuit with unknown resistance, so this is the situation. When we switch on it, then it is in closed circuit condition. Then L2 will be obtained. So here we'll do it like this: R equal to L1 by L2 minus 1 into R. So L1 is 260 upon L2 is 190 minus 1 into 40. Well, I have chosen these values. So so it is now approximately, if we divide both of them, it will be 1.2 mm, 3, I guess. And 6 approximately. Actually, by rounding off, it will become 7. You can calculate it of your own. Then 1.37 minus 1 is 0.37 multiplied by 40. So 37 fours are 288. I think so. 288. Oh, sorry, 288. 148 actually. 148. 148. So 148 and 10 will be there, and then 2 point places. So I'm putting that also. So this is the answer. Maybe my calculation are somewhat, I have done it just orally, so there can be slight error, but that is accepted also. A potentiometer wire of length 1 meter has resistance 10 ohm. It is connected to 6-volt battery in series. Oh god, okay. So here we have to draw its circuit also. This is, and a series resistance is also there. So here it is 5 ohm, here it is 10 ohm. Actually, I have just collected all type of possible questions, so you need to just practice these questions and find similar type of question. If any other type of question comes, just either overlook it, or you can suggest that question to me, and if it worth it, then I will make a video on it. If because some publishers sometimes make some questions which are out of context, so it is not a wise thinking to go after those questions. But if those questions are of CBSE standard, NCRT standard, I will definitely go for it. And actually right now our main target is to focus on these upcoming exams. All right, so null point is at 40 centimeter and 1 meter length is given. I'm writing it 100 centimeter. Okay, so let's see what entire this situation is all about. Um First thing we need to understand is to find, okay, I'm writing AB, and here J. All right, so in driver cell circuit, first part, as I told you, this part is not used, but in such type of questions where where this type of things are given, resistance of this wire and that, and we don't know EMF of this cell, and no other clue is there. So what we have to do in driver cell circuit, V equal to I R1 plus R2, that is 6 equal to I 5 plus 10, that is 15. So I equal to 6 by 15. And now, okay, resistance of AJ portion. See what I'm going to do. It is not Raj. Resistance of AJ portion is, we know that that 10 ohm resistance is of 100 centimeter. See what I'm doing. I'm doing it unit with unitary method. Actually, 100 centimeter is equal to 10 ohm. 100 centimeter wire has a resistance that of 10 ohm. So 1 centimeter will have 10 by 100. So 40 centimeter will have this. That is equal to 4 ohm. Now we will find VAJ, which is equal to I RAJ. I is 0.4, R is 4, 1.6 volt. And finally, this VAJ is equal to E, and which is equal to, okay, that's all, which is equal to 1.6 volt. So actually in this question we had to find potential difference across AJ, and that would be the EMF of the cell. What were the steps? First find current through this driver cell circuit, then find resistance of this portion, and then find potential difference of this portion, and that potential difference will be the EMF of the cell. Right, the principle of working of meter bridge, once again I would suggest you to refer to my video, and there is explanation of its working and all that. So I'm just drawing its diagram so that it would be easier for you to understand the concept. So, and a cell is there. So this is what a meter bridge circuit is all about. So here is A, here is D, here is C, and B is somewhere here. It is 100 centimeter long wire generally. If this is L, then it is 100 minus L. Why broad copper strips are used in meter bridge? So I'm 1, 2, 3, and 4. So second is why broad copper strips are used. To first thing, copper strips are used for internal connections. But why they are broad? To offer negligible resistance. Second, why Constantan or Manganin prefer to make meter bridge wire? So third point. Okay, there are several reasons. First reason is high resistivity. It has high resistivity. I'm writing it in short, but it has higher resistivity, so not too long wire is required for the purpose. If we take a very good conductor, then we have to take very long wire to encounter that effect. So it has higher resistivity, and its temperature coefficient is low. So it is immune to temperature changes. And fourth point is why null point is required to be obtained in the middle to minimize error. Uh, to balance the circuit perfectly. Obtain balance point at J such that AJ is 40. Find R ratio X. So very simple it is. R by X is equal to L by 100 minus L, that is 40 upon 100 minus 40, that is 62 by 3. That's all. R is to X is 2 is to 3. If both are interchanged, then how will position of null point change? If both are interchanged, then AJ will be equal to AJ will be equal to 100 minus 40, that is 60 centimeter. That is balance point will also balancing length. Balancing length, I'm using shortcut, will be interchanged. To maintain equal ratio, how will position of null point change? So will be interchanged, and that's all. So we have given the value, so no need further explanation. What does the term end correction in meter bridge circuit mean? Okay, so sometimes meter bridge wire is not in direct contact with connecting copper strips. So balancing lengths should be taken from the proper contact of wire and metal strip. This causes an error to compute balancing length and hence resistance. So how is it corrected? If balancing length is L, then the correction part, say delta L, should be added to it. Otherwise, ensure balance point must be just at the middle of meter bridge wire. So what happens actually if this is that metal contact and wire is connected? So here is the screw and they attach it to this screw. So it is not definitely in contact with this metal strip at this point. So this is that error term, delta L. Or one more thing can be done. Weld copper strip and meter bridge wire. This is other thing. If it is weld here, so we can definitely say that okay, from here we have to measure the length. Second thing, how will balancing point be affected if position of battery and galvanometer are interchanged in meter bridge experiment? So no change at null condition, as resistances are already in same proportion. So that's it. See you in the next video that will include Kirchhoff law.